All right, so this is going to be the lecture over slides 16 through 30. It's predominantly looking at the chi-squared test and quadrat sampling. So to start, just kind of wrapping up where we left off talking about ecosystems. Ecosystems are a community, but it also includes the abiotic environment. So that abiotic environment is going to include water and air, rocks and temperature, pH, light, and humidity. And those last four in particular, but especially temperature and humidity, are going to influence plant life in a community. So in order to classify organisms, scientists are going to look for patterns and group those organisms together according to those patterns. We can measure both abiotic and biotic aspects of the environment and then determine the frequency and distribution of a species. And we have some systematic sampling techniques to do that. The one that we're really going to focus on today is quadrat sampling. So that is one of the skills in this unit. Quadrant sampling, you need to be able to test for the association between two species using the chi-squared test with data obtained by quadrat sampling. So quadrats are square sample areas. They're often marked by a quadrat frame, which is what you can see in the picture on this slide. And quadrat sampling is going to involve repeatedly placing a quadrat frame at random positions in a habitat and recording numbers of organisms present. So scientists literally just kind of chuck it like a frisbee in the environment that they are sampling and then measure the frequencies of the organisms in that frame. The goal is to obtain realistic estimates of population sizes. And it's not very useful for motile or organisms that move. So if something can move around like a human, it's not very helpful to try and measure a 1 meter squared box and try to catch information from motile organisms. All right, so this image here on the left-hand side is just kind of showing how you would count. If we were not in the middle of a pandemic, we would be able to go outside and actually practice quadrant sampling, and you would see that you can count something if it's mostly in the square, and you wouldn't count it if it's mostly out of the square. You can see that there's types of sampling distributions, and I would recommend that you pause this video and watch the video demo on this slide here. I don't have the audio connected to my screencast from the computer, so you wouldn't be able to hear it if I played it. So just pause this video and watch the video demo of quadrat sampling in grassland ecology. And then you'll come back here, and I'm going to continue on here so that we can talk about the chi-squared test. So chi-squared testing is basically a way to check and see if something is statistically significant when discussing the results of an experiment. So there are, when we look at the chi-squared test, the first thing you need to do is identify the two hypotheses. You have the null hypothesis, which is H with a little sub-zero there, and that is the belief that there is no relationship. For example, that two means or two averages are equal, or that there is no association or correlation between two variables. And then the H1 or the HA is called the alternative hypothesis, and that's going to be the belief that there is a relationship. So that would be saying that two means are different, or that there is an association between two variables. So second step of a chi-squared test after you've identified the hypotheses is going to be to draw a contingency table of observed frequencies. This is going to be the data that you actually observed when doing your quadrat sampling, or when doing your sampling in general. It doesn't have to be a quadrat. We're just learning specifically with quadrat. After you get the observed frequencies in a data table, you're going to calculate the expected frequencies, or capital E, for each of the possible contingency table scenarios. And that is going to have a little equation here, as you can see on the slide. It's going to be the row total times the column total, and then you're going to take that number and divide it by the grand total. So just to actually back up here to look at this table, you can see that we have a row total times the column total, and then it would be divided by the grand total in the bottom right-hand corner. Okay. After you do the expected frequencies, you're going to calculate the number of degrees of freedom There's an equation for that. DF is how we abbreviate degrees of freedom. And you're going to take the number of rows minus 1 and then multiply that by the number of columns minus 1. And that will be your degrees of freedom, which is going to be a number that we look at our table in order to determine kind of what our critical value is going to be. And this is the table that you will look at, actually. So if you look on the the left-hand side, the first column, it says DF. So if you calculated 1 degree of freedom, you would go over, and we pretty much always are going to use 0.05 for that p-value. That just means we're looking for 95% statistically significant. So if you had 1 degree of freedom, and we're looking at 0.05 for the p-value, you would be looking at a critical value of 3.841. And we'll talk more about that value and how it gets used in the next slide here. So you've got the critical value, it's 3.841. We're just going to kind of keep that in our back pocket. And then you're going to calculate the chi-squared value. There's an equation for that. Chi-squared is represented by the x squared there. So we've got this equation here. You can see it's observed minus expected squared divided by expected. So once you calculate that, you will compare the chi-squared value with the critical value. And you're looking for kind of two options here. If chi-squared is less than the critical value, then you accept the null hypothesis, which means there is no association between the variables. If the chi-squared is greater than the critical value, then you reject the null hypothesis, which means there is a significant association between the variables. Another way of saying reject the null is accept the alternative hypothesis. But typically, in biology, we like to say accept the null or reject the null. We don't necessarily address the alternative hypothesis. Okay, let's go ahead and work through this sample problem. So we are looking at a sample scenario. We are looking on the rocky seashore, like Southern California, where I'm from. And we're going to be looking at quadrant sampling and the chi-squared test that comes as a result of the data. So the presence or absence of 2 species of scallops was recorded in 50 quadrats that are 1 meter squared in size on a rocky seashore. The following distribution pattern was observed. And that distribution pattern is in this square over here, this rectangle. So you can see 6 quadrats had both species, 15 quadrats had the king scallop only, 20 quadrats had the queen scallop only, and 9 quadrats had neither species. So in a chi-squared test, step 1, identify the hypotheses. So we got to distinguish between these 2 distinct possibilities. So we always need 2 contrasting hypotheses. So our null hypothesis is always going to be that there's no relationship or association. And our alternative hypothesis is that there is a relationship or association between the 2 species and where they're located. Step 2 would be to construct a table of observed frequencies. So you can see we've got the queen scallop on top and the king scallop on the right. And if they were both present, we would be marking that number in the top left-hand empty spot there. And if the queen scallop was absent and the king scallop was present, we would be filling in that second top spot, the second column top spot. You are just pulling the numbers for this table from this rectangle talking about the quadrats. So the number 6, because both species were present, would go in that top spot. So I'm going to just go ahead and fill this in for you so you can see the numbers right here. And I would pause this video now and just check and see that that all makes sense to you. You can see that the totals were added up. Pretty basic though otherwise. Next thing you're going to do is calculate the expected frequencies. So the table the table that we're going to construct is not just an expected frequency table. It's going to have the expected distribution, and we're going to immediately compare it to the observed. So I'll show you that table on the next slide. It just makes everything a little bit easier when you get to the final calculations. But we are going to follow this equation that I just blocked. There we go. Expected frequency is the capital E, and that's again going to be the row total times the column total, and then you're going to take that number and divide by the grand total. So we're trying to get an expected frequency for the queen scallop and the king scallop. And then we'll do that calculation on the next slide, but I just want to talk about step 4 because that's also going to happen at the same time on the next slide. Step 4 is going to be to construct the table of observed and expected frequencies, and you're going to apply that chi-squared formula, which we have on this slide. So you can see that E symbol, if you're taking higher level math, you know that's the sum. O is observed frequency, E is expected frequency, and obviously the x squared is just how we represent chi-squared. So the calculations can be broken down for each part of the distribution pattern to make the final summation easier. So here is the table that we're going to fill out. Some of this information we're literally just copying from our observed frequencies table. So any section that says O, so like over here, O, we're just copying that information, and right down here as well. We're just copying that information down from our first table. The E section is our expected frequencies that we're calculating. So again, row total times column total divided by grand total. And then once you have your O and your E, you can actually plug it into that chi-squared test. So you can go ahead and do the separate calculations for the presence of both the king scallop and the queen scallop, the absence of one with the presence of the other, the presence of the queen scallop, the absence of the king scallop, and the absence of both. So I'm just going to put all those numbers in, and oh, I'm sorry, I didn't make the table invisible, but they're all in the right spot. So what you need to do now, because this is a sum of these observed minus expected squared over expected, the chi-squared, you would need to actually add up the numbers 2.20, 2.38, 1.59, and 1.73 in order to get the sum of all those numbers, which is then going to be your chi-squared value. So when you add those all up, you should get 7.90. So that is our chi-squared value. So step 4, step 4.5, if you will. The next step is going to be to determine the degrees of freedom. So remember, in order to determine if the chi-squared value is statistically significant, you have to find your degrees of freedom. And then the degrees of freedom is a mathematical restriction that designates what range of values fall within each significance level. So it's going to be calculated from the table of frequencies using this formula here. So again, number of rows minus 1 times number of columns minus 1. So we had 2 rows, so 2 minus 1 times 2 columns minus 1. So that ends up being 1 times 1. So our degrees of freedom is going to be 1. And note that when the distribution patterns for 2 species are being compared, the degrees of freedom will pretty much always be 1 because we're just looking at 2 species and comparing them. So 1 degree of freedom there if you do the calculation. Last thing we need to do is identify the critical value, which is also called the p-value. This is the final step, and you have to apply the value generated to a chi-squared distribution table to determine if the results are statistically significant. So the value is considered significant if there's less than a 5% probability, or p is less than 0.05, that the results are attributable to chance. So that's why we use the p of 0.05 for our chi-squared tests. The table that you'll need to use is on a previous slide, but it is, and this is probably going to be backwards, it is this table here. Sorry if that's kind of hard to see. And I kind of marked out the 0.05, and you can see that, I know it's backwards for you, but the degrees of freedom are 1. So if you look in that section, that means our critical value is 3.841. So critical value of 3.841, chi-squared value of 7.90. So in summary, our x squared, our chi-squared, is 7.90, which is greater than 3.841. If the chi-squared is greater than the critical value, you reject the null hypothesis, which means there is no significant difference between the observed frequencies and the expected frequencies. And that means that these two species do not tend to be present in the same area, so we can infer a negative association between the 2 species. So again, chi-squared was greater than the critical value of 3.841, so we rejected the null hypothesis, meaning there is a significant difference between what we observed and what we expected So it's a negative association, oh my gosh, tongue twister, a negative association between the chi-squared, between the queen scallop and the king scallop. You are going to now work on your chi-squared practice worksheet. There's 2 problems to work through, I believe, maybe 3. So as you're working through those, if you have questions, refer back to this video, refer back to the slides in the unit, ecology unit part of Schoology. Thank you.